In this video, we'll be proving Theorem 5.1.1, which told us that for a region like this, where the region that's bounded between y equals f of x and y equals g of x, where f is the bigger curve, between a and b, the area would be the integral from a to b of f of x minus g of x. All right, so we'll prove that right here. Proof of Theorem 5.1.1. So the way we'll set it up is going to be quite similar to what we did in chapter 4. It's just that in the end, instead of defining something new, we want to relate it back to the definite integral because we've learned in the last chapter how to compute these efficiently using antiderivative. Right, so let's approximate the area of the following region using n rectangles. All right, so I have my region bounded between y equals f of x and which color was I using? Green for the top and blue for the bottom. All right, so I'm going to use n rectangles. All right, so here are my division on my interval. And for each one, I'm going to use, let's use right-hand point since we're used to it. So I'm going to use this height to build my rectangle. So it's going to look like this. So that will be my first rectangle. I'm going to do the same thing over the second one. Sorry, a bit lower. And so you can see the rectangles don't have the same base now. They're moving up and down as well at the bottom. All right, and you keep going like this. So the idea is very, very close to what we did in the last chapter, in chapter 4, except that now the bottom is not a straight line, and so the bottom of the rectangles moves up and down depending on the bottom curve. All right, so for each small rectangle, if I have n rectangles, the width will be the total length divided by n, so it's still b minus a over n. Now the heights are different, right? The height depend on both curves. So for example, this one would be f of x1 minus g of x1. So the height of the k rectangle would be f of xk minus g of xk. So the area of one rectangle, that will be width times height, so it will be b minus a over n times f of xk minus g of xk. All right, so each of these rectangles would have this height where xk changes. And so when we actually want to approximate the area, we'll be adding them all up. So from the first rectangle to the nth rectangle, width times height. But that's, I mean, if I write it this way, maybe you'll see it more. It's the usual width, and then xk, but not in f minus g. So it actually gives you a new Riemann sum, a Riemann sum of the function f of x minus g of x. I'm sorry, this is a tiny bit low. Let me hike it up. All right, so it's the Riemann sum of the function, let's call it h, which is f minus g, over the interval ab. All right, so when we apply this process, we get a Riemann sum, just a Riemann sum of a function that mixes f and g. That makes sense. And so to get the area, we let the number of rectangles n go to infinity, and so we'll have the limit as n goes to positive infinity, summation delta x f of xk minus g of xk. And so really what we're getting is an integral over AB, because that's the interval here, and we're integrating this function. So f of x minus g of x. All right, so something interesting is happening here where the argument is actually telling us that if we want to compute this area here, it's going to be the same as if we actually kind of bring all of this down and flatten it, like we're pushing here, and all the little sticks are coming down. And so what it's telling you shows that the area between, let's call this y equals f of x and y equals g of x is the same as the area between y equals f of x minus g of x and the y-axis, the x-axis, sorry, y equals 0, right? Because the rectangles that I would be using will be exactly the same rectangles, just shifted up and down, right? So my approximation would be the same. This rectangle has the same area as this one. The next rectangle over will have the same area as that one. Okay, so we can use what we've done in the previous chapter. We just use it on a slightly different function, and what we're getting is the area of this more complicated region. All right, so we'll start doing more and more examples with more complicated functions in what follows.